in this lesson, we are going to look at some types of functions. Previously, we have already learnt about functions. Now, what is a function, domain, range, etc. A function is nothing but a relation from a set A to a set B such that every element is in A is mapped to exactly one element in B. Okay. So now we know that A is the domain and B is the codomain, and we have learned some of the basic concepts related to functions. Now we are going to look at some types of functions. The first type that we are going to look at is called a 1-1 function or injective function. Okay. Now what is a 1-1 function? Well, we know that if f is a function, if you drew the diagrams for the set A and set B, you know that every element in A must definitely be mapped. It must be mapped to only one. You can't have two arrows going out from one element. But you can have two elements being mapped to the same image in B. Now, what the 1-1 function, its definition is that you don't have this kind of mapping. So which means if, so simply put, if f of x1 equals f of x2, then x1 equals x2. If I have two things being mapped to the same element, then the original element itself must be the same. Now, so which means this is not allowed in an injective function. In an injective function, to one element there can be only one arrow. Okay, so you can have only one arrow leading into every image in the codomain set B. Okay, an easier way of defining this is this condition. Okay, now what are some examples of injective functions, right? Is it very common? First of all, should all functions be injective? No, we know that for a function, from every element there should be only one arrow, but into every element it's okay to have multiple arrows. But in this case, so let's look at some examples. There are also functions which are not injective. So let's take an example. So example, okay, let's say f of x is equal to 3x plus 5. Suppose I have a function like this and somebody says that let's check whether it's injective. All I need to do is to see whether 3x1 plus 5 equals 3x2 plus 5 will imply what? If I have this equation, then I can cancel 5 and show that x1 equals x2. That means two different elements cannot be mapped to the same same image. On the other hand, suppose you take f of x is equal to x square. Okay, simple example. Suppose I have x1 square is equal to x2 square. Okay, now this clearly means that x1 is plus or minus x2. So x1 is equal to x2 or x1 equals minus x2. So that means this function is clearly not injective. But this is not the only example of injective functions. We can have many other example of injective functions. So let's take some other example. If you take, for example, trigonometric functions, we know that in trigonometric functions, let's take sin x for example. Will it be something like injective? Well, you can see that for many different x values, the y values are the same. For example, for x1 here, x2 here, the y value is the same. We know the trigonometric functions are periodic. So for many different x values, you will get the same y value. But how can you make it injective? Well, if you say that I am going to take only values, okay. So for example, so let's say you take sin x. So you take sin x from minus pi by 2 to pi by 2. So you can see that it goes from minus 1 till 1. So suppose you define f from minus pi by 2 to pi by 2, to 0, 1. Sorry, minus 1, 1. Okay. So this is set A, this is set B, such that f of x is equal to sin x. Then you can see that within this domain, that is minus pi by 2 to pi by 2, if two values give, if sin x1 is equal to sin x2, will imply x1 is equal to x2, because there aren't two different x values that can give the same y. If you draw a line parallel to y-axis, it will cut this portion of the curve only at one point, or you draw a line here, it will cut only here, right? So you can sort of modify the domain in such a way to make it injective. Okay, so you can, of course, we can come up with many more examples. For example, if you take f of x is equal to e power x, right? That's also an injective function, because e power x1 is equal to e power x2 will imply x1 is equal to x2. Okay. Again, we can draw the graph and show the graph of e power x at, so this will at 0 it is 1 and then it goes like this. So if you take any line parallel to the y-axis, suppose I draw a line here, I want to find, let's say this is some 1.9. Okay, I want to find e power x is equal to 1.9, there is only one value. Okay. Now you have to understand that the function itself, e power x, does not allow negative numbers. Okay, e power x is always positive, but that consideration doesn't come into this definition. We are only bothered about e power x1 is equal to e power x2. If that is given, can we say for sure x1 equals x2? Yes. Okay, so this is the definition for injective function. The next idea is what is called an onto function. Onto function is also known as a surjective function. Okay. Now what is an onto function? An onto function is one where if you define the domain and codomain, every element in the codomain has a pre-image. It's an image of something. There's an arrow leading into everything. Okay. Now it is possible that two things are leading to the same. It's possible. As in, onto functions need not be one, but they cannot have any element isolated in the codomain without any pre-image. Okay. So again, suppose we say f of x. Okay. So let's say we take y is equal to f of x. Like that's how we represent the function. So the values here are y and here are all x. How do we check if a function is onto? Well, what we are going to say is, if the codomain, suppose you say f is from set A to set B, so codomain is set B. Okay. Now for every y belonging to B, we should be able to find that exists an x belonging to A such that f of x is equal to y. If this condition is satisfied, then we can say that the function is an onto function or surjective function. Again, let's take some examples. So let's just take the same example that we took, f of x is equal to 3x plus 5. Now is this an onto function? Now for this we first have to define what is the domain and codomain. So we are going to say f is from R to R, that is real numbers to real numbers. Okay. So let's see if this works. So let's say that we want to say y is equal to 3x plus 5. How do we find out if a function is an onto function? Now, yeah, well, this condition is all fine, but really what you need to do is, given a y, you must be able to somehow prove that the x exists. So what is the best way to do it? Actually calculate the x and show this is the x that will give us the y. Okay. So what we will do is, So we will say y minus 5 is equal to 3x, and therefore x is equal to y minus 5 by 3. Now what we can say is, given any y as part of the codomain, can we find an x? Yes, there is no violation. It's not like if y equals 5 it will be some division by 0 or some problem, nothing like that. So every single real number in the codomain we can substitute here and we can back calculate the x, and therefore that means this condition is satisfied. Actually the other way of stating that condition is that the codomain of this function is the same as the range. Codomain equals range. And the reason I am saying this is, earlier when we learnt about domain and range of functions, we already saw that if you're given a function like this, how do we find the range? We substitute y equals this and we try and calculate and see which y's are not allowed. That's what told us what values will be exempt from being part of the range. Well, if no value is exempt, then every element in the codomain is part of the range, which is basically the way of stating another condition to check if a function is onto. Okay, so now let's look at a couple of other examples. Let's take this example. So we took the other example, f of x is equal to x squared, right? So the question is this function an onto function? We already saw that it's not a 1-1 function, okay, because minus 3 whole squared is the same as plus 3 whole squared. Is this an onto function? Now that depends on how you define your domain and codomain. If you define f as from R to R, then it's clearly not an onto function. Why? Because suppose that means all real numbers you can consider. Now is there so y is equal to x square. Suppose I put y is equal to minus 3. Minus 3 is equal to x square. Can you find a real number satisfying this? Clearly no. But on the other hand, suppose I say f is from all real numbers to R plus, that is all positive numbers including 0, okay. So union the element 0. This is only positive real numbers and you add 0 to it. Now, is this an onto function? For every element in the codomain, can we find, for example, suppose you have y is equal to x square, okay. Now I say y is equal to, let's say 3. 3 is equal to x square. What is x? X could be root 3 or x could be minus root 3. Now you say there are two elements whose image is 3. Is that a violation for onto? No. Onto only asks, for every element have I found a pre-image? Then I am happy. Well, I have two pre-images, that's okay, that's not a problem, okay. So this will be an onto function, whereas this will not be an onto function, okay. So the big idea here is that for onto functions, we have to be very careful about what is the codomain we have defined, okay. So let's take another example, last example. Let's say, suppose I take that f of x is equal to, f is from R to R, okay, and suppose we say that f of x is equal to simply 1 by x, okay. Is this an onto function? Well, let's see. First, we cannot define it from R to R because at x is equal to 0 the function is not defined. So the domain itself cannot be R, it has to be R minus 0 to R, okay. Is that clear? Now because x is equal to 0 is not allowed, okay. Now it looks like you can put any value of x and you will get values of y. It looks like it's an onto function, but we have to be careful. So we have to do it the same way. Y is equal to 1 by x. So given any y, can we find x? That means x is equal to 1 by y. But x also has the same constraint that y cannot be 0. Think about it. Not only can x not be 0, 1 by x also cannot take the value 0. Why? For 1 by x to take the value 0, x has to be exactly infinity. But, or I mean, if you sort of assume that 1 by infinity is 0, but we already know that infinity is not a real number with which you can do mathematical operations. Therefore, this is not an onto function because y equals 0 is not allowed. That means the 0 which is part of the codomain is actually not getting mapped, okay, from any pre-image. No arrow is leading into 0, because there is no number called infinity or minus infinity on the left hand side, which means this is not an onto function. So you have to now define your codomain also as r minus 0. If you do that, then it becomes an onto function. So you have to be very, very careful with what the codomain is for onto function. Okay. Now the last idea is a combination of both of these, which is a bijective function. So that is the third. Okay, this is both 1 1 and onto, or both injective and surjective. A function that obeys both these conditions is called a bijective function. Okay, so which means it has to satisfy both. F of x1 is equal to f of x2. So let's say f is a function from set A to set B. F of x1 equals f of x2 must imply x1 equals x2, and for every y belonging to B, there exists an x1, or for every y1 there exists an x1 belonging to A such that f of x1 is equal to y1. Okay, if both these conditions are satisfied, then we say it's a bijective function. Again, let's take examples. The example that we took earlier, f of x is equal to 3x plus 5, we found that it's both a 1 1 function as well as an onto function. Therefore it's a bijective function. Now one small sort of caution while calling these functions, a bijective function is also something where we know that if you draw this, what you will find is that there is exactly one arrow into every element, and there is no element left unmarked or unmapped. Okay, we know that on the left hand side definitely every element must be mapped, but no element can go to two things anyway, because that won't even be a function. Forget injective, bijective, etc., surjective. From one thing you cannot have two arrows anyway, just for function. Okay, but no two things are going to the same because it is 1 1, and nothing is left unmapped because it's an onto function. That means a bijective function will be very neat. There won't be crisscrossing this thing. Every element will get mapped to exactly one thing, and what we call this is a one-to-one correspondence. Okay. Now, in terms of terminology, we have to be a little careful because the term 1 1 and 1 to 1 look very similar, but 1 to 1 correspondence means it's both 1 1 and onto. It's a bijective function, whereas 1 1 just means an injective function. Okay, this is just something to keep in mind. Okay, now what we can find is that functions like f of x is equal to 3x plus 5 are bijective functions because we already found that they are both 1 1 and onto. In fact, what we can say is we can do a more general f of x is equal to ax, sorry, the same a and b cannot be used. It's a ax plus b, where a and b are any real numbers, is a bijective function. Okay, we can also come up with other examples. Now, for example, let's take f of x is equal to e power x. Okay, is it a 1 1 function? Is it onto? Is it bijective, etc.? Suppose we ask. The question to the thing to specify is what is the domain and codomain. If you say from real numbers to real numbers, it won't be. Why? Because we know that the plot itself, okay, only covers positive values of y. There are no negative values of y in the plot at all. E power x can never be negative. So if you define f as from R to R, domain is real numbers, it's fine. All negative x, positive x, everything can be covered. But if you define it as R to R, it's clearly not onto. We saw it's 1 to 1 because f of x1 equals f of x2 equals e power x1 equals e power x2 implies x1 equals x2. But it's not onto because if you suppose you ask minus 3 is equal to e power x1, what is x1? No such value exists because negative part of the graph is not covered at all. On the other hand, suppose you define this as f of x is from R to R plus, okay. In fact, R plus only, not even 0, because can any value make y 0? Any x? In fact, only minus infinity can, but minus infinity is not a real number. As x tends to minus infinity, y tends to 0, but y is never going to touch 0. So suppose you make R to R plus, then you will find that it is a onto function. It's already 1 to 1, so it's a bijective function, which means e power x1 equals e power x2 will imply x1 equals x2, and for every y is equal to for every y belonging to R plus, we can find y equals e power x1. In fact, the way to find the x1 is simply log y, and since y is only positive numbers, you are always allowed to take log as a natural log. Natural logarithms you take, you can find the value of x1. So we've actually found the value of x1. Okay. So depending on how you define the codomain, we saw that onto property can be attained, and the same logic extends for bijective functions also. Okay. Now let's also take a case of a trigonometric function. Suppose I say f of x from minus pi by 2 to pi by 2 to all real numbers where f of x is equal to tan x. Is it a 1, 1, on 2, etc.? Let's see. F of x is equal to tan x. We know that tan x function from minus pi by 2 to pi by 2, if you draw close to minus pi by 2, it's almost minus infinity. So it starts from there, it's asymptotic to the x is equal to pi by 2 line. Okay. So now this is the curve of tan x. Now this curve, this function is both 1, 1 and on 2. Why? Because if you draw a line, does it cut two values of x? No, there's only one value. For every positive there's a value between 0 to pi by 2. For every negative y, there's a value between minus pi by 2 to 0. Okay. For every real number, will you be able to find an x that maps from here to the real number? Now that's a more tricky question that requires us to know a few other ideas, in fact related to calculus. I won't go deep into that. All I'm going to tell you by way of convincing right now is, you can imagine that for values very close to minus pi by 2, tan x tends towards minus infinity. Similarly, very close to pi by 2, it tends towards infinity, and it's a continuous function that does not have any break at all, even though we have not clearly defined these terms and all that so far. So that means there is no jump or break in this function. So every single real value from minus infinity to infinity will be covered as part of this journey of tan x, and therefore we can say that f of x that goes from minus pi by 2 to pi by 2 to real numbers, tan x is a bijective function. Of course, it depends on what is the domain, what is the codomain, etc., etc. Okay. So we can bring trigonometric functions also into the ambit of onto or 1 to 1, 1 or bijective functions, but by defining the appropriate domain or codomain. Functions like these are obviously bijective. Okay. So just to summarize, we have learned three kinds of functions: 1, 1 or injective, onto or surjective, and 1, 1 onto and 1, 1 onto as same as bijective.